we continue our talking about how molecules are going to move across the membrane, we've already talked about the concentration of molecules on the two sides and how that affects the direction that molecules want to move. So they want to reach equilibrium or equal concentrations on the two sides. Another thing that plays an important role in molecule movement is going to be membrane potential. Membrane potential is the voltage difference across a membrane. So by voltage difference, we're basically talking about the charge difference that we have on the two sides of the membrane. Generally speaking, the cytoplasm is going to be negative in comparison to outside of the cell because you have extra anions inside the cytoplasm. Now, just like the concentration gradient causes molecules to move until they even out those concentrations, the membrane potential is going to cause molecules to move in a way so that they become neutral on the two sides of the membrane. So we say that this does act as an energy source because molecules want to move to get to that neutral point. If we put it all together, we call the combination of forces acting upon an ion, helping to decide which way it's going to move, the electrochemical gradient. So the electrochemical gradient has the chemical force component, and that's the ion's concentration gradient, the fact that it wants to go high to low. And we also have the membrane potential component, which we call the electrical force. So the desire to basically reach that neutral point. If we look at this picture right here, we've got a concentration gradient. Notice that in the cytoplasm here, we've got low concentration, and outside we have a high concentration. And these hydrogens here would want to move from high to low. Now these hydrogens, H pluses, they actually are just protons. They don't have any neutrons or any electrons there. So we do call them protons a lot of times, and you'll see that term used more and more as we get into later chapters. These hydrogens would have difficulty getting across the membrane because they have a charge, so they're not going to pass through that hydrophobic core easily on their own. As well, we've got extra negative charges in the cytoplasm in comparison to the outside of the cell, or the extracellular fluid. So if we look at this little proton pump here, this proton pump is going to take a hydrogen from inside the cytoplasm, and it's going to move that hydrogen across the membrane. So it's going to dump it on the outside of the cell. This is going to be moving it from a low concentration to a high concentration, which is why we've got to have the involvement of the ATP up here. So we're not going to be able to move that from a low to a high concentration without actually using some ATP. When we do that, we will go from having one hydrogen inside to 5 hydrogens outside. We'll end up now with 0 and 6. So we will have an even greater difference in concentration on the two sides of the membrane than we had before. And in addition to that, we're going to make the charge difference on the two sides of the membrane even greater because we're removing a positive charge from the inside and we're adding a positive charge to the outside of the cell. Well, any transport protein that moves something that's going to alter the charge or the voltage across a membrane, this is going to be called an electrogenic pump. So the proton pump here is just one example of that because that hydrogen that it's moving is affecting the charge that we have. Now if we look at why it would actually do this, this is going to be important for what we call CoTransport. And now we have kind of a long definition here for CoTransport, but we'll take it one bit at a time. So the first part states that this occurs when the active transport of a specific solute, if we stop right there, that's the active transport of our hydrogen that we looked at on the previous slide. So notice we're taking the hydrogen from the low concentration and we're moving it to a high concentration. If we do that, we're using this ATP, and that is going to be active transport. Now the reason that we're going to do that is because if we have a big difference in hydrogen concentrations on the two sides of the membrane and charge differences on the two sides of the membrane, the hydrogen would really like to flow back across the membrane and get to the cytoplasm side, which is shown as the tan in this picture. Now, it is going to have trouble getting across that membrane, as we said before. So here we have a second transport protein. This one's called the sucrose hydrogen cotransporter. It's an example of one. But this is able to bind to the hydrogen and carry it across to the other side. Now, when it is flowing in this direction, this is basically a facilitated diffusion. Notice that we are going from high to low, and we're just using a carrier protein to make that happen. Now, the second part of this says that this active transport is going to indirectly drive the active transport of another solute. If you look, we have a second molecule here, sucrose. Now, sucrose is in a low concentration out here, and it is a high concentration inside the cell. Because sucrose is a beneficial molecule for the cell, it makes sense to bring more of it into the cell and accumulate the sucrose. That would be active transport to move it from low to high. So to get this moved from low to high, we're going to basically piggyback the sucrose across. It's going to bind to this carrier protein at the same time that the hydrogen does. And now as the hydrogen is flowing across the membrane, we're going to drag the sucrose at the same time. That's what we mean by cotransport. Basically, we've got this second active transport which will be powered or driven by a concentration gradient. This works very similar to water rolling down a hill and causing a water wheel to turn. It's just because that water is rolling down the hill anyway, we have it turn the wheel, and then we can get some electricity out of that and use it to power things. So this is pretty common inside the cell to use cotransport, active transport of one solute, in this example the hydrogen, that indirectly drives the active transport of a second solute, which is going to be the sucrose. Okay, those are ways that we move individual molecules one at a time. Now, sometimes the cell has need to move a lot of molecules at once, so bulk transport. So this can be many molecules or maybe just a few large molecules at one time. We kind of already saw this in chapter 6, although we didn't really call it bulk transport. We saw a lot of vesicles moving around, and those vesicles were basically cargo carriers. So within those vesicles, which are little bubbles of membrane material, you can have any number of things actually packaged inside of them. And then as long as we can move that vesicle around, we're actually moving the contents. So this is used in several different ways. It can be used to have things exit the cell, and this is called exocytosis. In this diagram, that's exactly what we see happening. We can have vesicles come from the ER, which contain materials inside. We could fuse those with the Golgi. We could pinch off the vesicles again, but in any case, we have a lot of things included in this little vesicle. If we fuse this with the plasma membrane, anything that was inside that vesicle is now going to be dumped outside of the cell. So in one step, we've basically taken a bunch of stuff that was inside the plasma membrane, and now we've dumped it outside the plasma membrane. Notice that anything that happened to be inside that vesicle is going to get dumped across the membrane. Now, we can also take things into the cell using the same kind of process. If you can just envision kind of turning the arrows around, we would be moving things inside. Now this is called endocytosis. So in endocytosis, we're bringing things into the cell. This would be macromolecules or a bunch of molecules at once, and this is going to be through the formation of some new vesicles. Now, there are several different examples of endocytosis, and they're named in different ways. This top one here is what we would call phagocytosis. Phagocytosis, basically you're engulfing food. This is what an amoeba does. So in this case, you actually have some projections, which are called pseudopodium, which reach out and around a food particle. And when they do this, that basically pinches the vesicle off now to the inside of the cell, and we have a food vacuole, which we could then fuse with a lysosome or something similar. So phagocytosis, we're actually reaching out and around something. If we have pinocytosis, we have a pinching in. So notice that there is kind of an enfolding of the membrane. Any molecule that happens to flow into that folded in area is going to end up inside the cell. Notice there's not a lot of selection there. So whatever happens to flow in, we're going to get inside the cell, good or bad. The last one here, receptor-mediated endocytosis, is one way that a cell can somewhat select what it brings into the cell using these methods. So in this case, we've got some little Y-shaped receptors. These bind to specific molecules, shown as triangles here. And if you have some triangles that bind to your receptors, you can pinch in that particular area, and now you know that you're getting triangles inside the cell. Now you're also getting some other molecules as well, so notice we've got some little green circles in there also. But we have had some selection as far as what gets brought into the cell. So you want to keep in mind that we can move lots of molecules at one time, or very large molecules at one time, across membranes using vesicles. So vesicles are just cargo compartments that can move from one area to the next, but also cause things to cross that plasma membrane or any other membrane inside the cell. And we also want to understand that we can move individual molecules at once, and that can be by active transport or passive transport. It may or may not involve transport proteins, such as carrier proteins and channel proteins. And we also want to understand what CoTransport is.